Hey everyone, we are Group 15 and we have been working on a DC to DC converter control. Solar energy systems are the main market we are targeting, and for good reason. The use of solar energy is consistently being both implemented and revolutionized. Once a feed-in tariff or power purchase agreement is introduced, the government and utilities cannot keep up with the rate at which people install solar. To prevent overloading, many utilities are beginning to incentivize smaller, more localized, residential installments of solar. In the USA alone, within the second quarter of 2019, there were over 600 megawatts of photovoltaic solar energy installed. The total capacity that we have installed in the US is expected to double in the next 5 years. Over the past decade, the cost of installing solar has dropped by 70%. This cost drop means that solar is becoming more and more affordable to the average American. Now that the market is addressed, we can see all this growth means we can contribute to capture some value in this market. The figure in the top left displays the common system for a residential solar installed with a battery. Within this current system, solar panels produce variable DC power. This power then flows into an inverter to convert the electricity into AC power for the grid or home appliances, some of which then needs to convert back to DC power for the appliance to run. This means a good chunk of the power from the panels get lost in conversions. Now there are some inverters, coined hybrid inverters, that can condition both DC and AC power, but they range 8 to 14 cents per watt DC more expensive than the standard inverter. And this additional cost can hurt a project's economics substantially. So the problem we are addressing is how can we implement a more efficient system that adds value to all our project stakeholders. To answer these questions, we agreed to build a DC to DC converter to eliminate conversion losses altogether. This solution will have an input of varying DC voltages from the panels, and we will condition these voltages to a desired output voltage for our DC loads or potentially a battery to operate on. After checking out different circuit configurations, we sided with a buck boost configuration for our circuit. We purchased an off-the-shelf buck boost converter that allowed us to focus on the controller for this circuit and tuning the PID to alter the duty cycle dependent on the varying input voltages. Additionally, we plan to test the stability of the circuit, as well as comparing our system to the common standard right now with a regular inverter, hoping to prove that the added value is worth the additional cost of our component.
DC to DC converters are currently being used in existing photovoltaic systems to take DC voltages from the photovoltaic system storage and convert it to a regulated different DC voltage output. Several configurations are available, such as the buck converter, the boost converter, the chuck converter. However, the buck boost converters will be specifically examined due to the configuration's ability to step up or increase and step down or decrease DC voltages. The buck boost converter is shown to the right in its generic configuration. The output voltage of the buck boost converter is shown by the following equation, where the output voltage is dependent on the duty cycle of the circuit. The behavior of the switch determines the circuit's duty cycle. Once the duty cycle is set at the switch, the output voltage of the circuit will adjust accordingly. The current configuration allows for a duty cycle to be set and to determine the output voltage dependent on the duty cycle of the switch and the input voltage set to the circuit. However, in its current generic configuration of any DC to DC converter, requires a controller to be added in order to allow dynamic control of the output voltage. In its current open loop state, the duty cycle needs to be manually adjusted in order to achieve different outputs. Adding a controller to the circuit that allows the switching signal of the circuit to the configuration allows for setting different desired output voltages and having the controller dynamically adjust the duty cycle of the circuit to achieve different output voltages. The controller will be designed using the proportional integral derivative, or PID, controller configuration. The equation shown here on the slide represents the PID controller in the Laplace domain. The three gain parameters in the equation, Kp, Ki, and Kd, are used to fine-tune the step response of the controller to a step input. The graph to the right illustrates a PID controller's response to a step input. The goal is for minimal transient and minimal overdamped or underdamped response. The PID controller will be designed using MATLAB and simulation. The buck-boost converter and the controller simulation, as modeled in Simulink, can be seen on the right of the slide. The gain parameters of the PID controller were automatically tuned using MATLAB. This closed-loop system allows for different desired output voltages through adjustments to the duty cycle of the converter. Simulated data was generated using PVSys, modeling photovoltaic system voltages in Philadelphia for an average month. The graph on the left illustrates the system's response to an input voltage of 24 volts with a desired output voltage of 12 volts. The graph on the right contains the system's response to simulated data that was generated using PVSys as previously mentioned. The data points in green illustrate the simulated data, while the data points in magenta illustrates the system's calculated duty cycle required at different switching frequencies.
There were several physical components involved in this project. To start, there was the buck-boost converter that would be in charge of stepping down and stepping up the output voltage. Luckily, the Drexel model purchased by the group also allowed users to regulate the output current to help circuit protection. The Arduino microcontroller used by the group would be involved with remotely and automatically controlling the buck-boost converter's output voltage and output current. For the Drexel model of the buck-boost purchased, the pulse width modulation that created the bucking and boosting of the output voltages and currents was done through a series of chips on the product's printed circuit board that would be controlled through the manual potentiometers on it. To remotely control a 3D Arduino, the manual potentiometers originally on the board were removed and replaced by digital potentiometers that were soldered on top of the original solder points. The group purchased wires rated for 16 AWG to be used for connecting the electrical components together, since these rated wires could withstand the expected currents that would be delivered throughout the system. In case there were irregularities in the current that produced high current values, 4-amp circuit breakers were added into the design to prevent equipment damage, in case the Arduino did not properly regulate the output current from the buck boost. Electrical loads were planned to be implemented in the testing as well, such as light bulbs that would be used to simulate energy usage throughout the day in a home. A battery was also planned into the design for storing energy when there was more solar energy coming into the system than was being used by the electrical loads. This energy was to be stored for later usage when the incoming solar energy was no longer present.
Here are some hazard mitigations and preventions that were used to build this system. Making sure that all the equipment ratings when conducting the physical experiment were compatible with all the equipment was one of the things that we needed. We also had to make sure that we had appropriate cable sizing, and we determined this by using the American wire gauge cable sizing charts to make sure that we had appropriate cable size to run within our system. We also had circuit breakers to prevent any overcurrent damage to the system. We also had to monitor the system to make sure that during the testing that anything that was not expected is happening. We also followed IEEE standards that will be mentioned later in the slide.
Although further evaluation is still required, the environmental impact of our product would seek to have a responsible supply chain process, including overseeing the reuse of common minerals such as mercury, lead, and chromium, and overseeing the recycling of our products at the end of life. With our product in the market, we would hope to increase awareness of climate change and increase responsibility for energy consumption. In addition to having a responsible environmental impact, our product would need to abide by regulations for safe usage, including IEEE 333 of 1980, which specifies implementing circuits and wiring of under 600 volts. Also, the entirety of the National Electric Code of the National Fire Protection Agency 70, or NFPA, will need to be followed. Some examples of codes within the National Electric Code include Article 690, which addresses photovoltaic systems that are not generating plants such as solar farms and are used in residential circuits. Also, Article 705 which addresses installation of one or more electric power production sources operating in parallel with another primary source of electricity. This would apply in our situation where it may involve DC to DC voltages as well as DC to AC, and also other local codes and standards would apply in regions where our controller would be implemented.
The group broke down the project into 3 components: simulations, microcontroller programming, and physical product assembly. For the simulations section, the group was able to simulate the buck boost operating throughout 1 year to see how the duty cycle and output voltages would fluctuate throughout the year. For the microcontroller programming, the group was able to get the Arduino to regulate the output voltage of the buck boost when certain signals were sent to the microcontroller. And finally, for the product assembly, the group was able to test out the extreme output values of the buck boost to gauge what circuitry protection would be needed and to see what happens when such voltage and certain current variations occur. The group also analyzed the microchip circuitry to understand how the pulse width modulation was occurring via the manual potentiometers on the circuit board. The group originally planned to begin soldering in the digital potentiometers to replace the manual ones over spring break. However, that was scrapped once announcements to stop the physical construction were given. Unfortunately, this project was cut short due to the COVID-19 virus outbreak. As instructed by the lead professor of this course, Dr. Fontecchio, all groups had to terminate all lab work conducted along with software simulations. For our group, this involved stopping the assembly of our final product along with the microcontroller, programming, and simulations being ran. All equipment purchased by the group has been stored safely on campus so that if this project is picked back up, the materials can be found all in one space. Initially, the group had planned to conduct more in-depth simulations involving equipment rated for higher loads that would be seen in an actual building. However, this idea was scrapped once the group was notified that all work, including simulations, were terminated.
For this senior project, Arduino Mega 2560 is used. The Arduino board contains 54 digital pins, 16 analog inputs, and 4 serial ports. This board contains more and better functionality than Arduino Uno, and it can simply be connected to the computer with USB port. The main purpose of the microcontroller is to adjust the voltage. For programming, MATLAB is used, and MATLAB provides the Arduino package. Arduino package is the MATLAB library that enables to communicate with the Arduino board. The user can read and write sensor data through the Arduino and immediately see the result in MATLAB. Using MATLAB and its Arduino package, Arduino board can be manipulated without compiling. The most beneficial of using them is to synchronizing collecting data and controlling the microcontroller. Using the data, MATLAB can create a graph and analyze them. This is a simple MATLAB script that voltage is controlled by a potentiometer. For saving file size, the video is uploaded on YouTube. There are 10K potentiometers, 2 red and blue LED are connected to the Arduino board. The potentiometer dividing voltage with rotating contact. Senior design schedule is designed as a Gantt chart. In the fall term, our team had a first advisor meeting, filled out PQA form, and studied a basic concept of buck-boost converter and others. In this term, we were mainly focused on understanding what previous senior design group had done and the concept of the buck-boost converter. In the winter term, the buck-boost converter were finally shipped, and our team conducted the component testing and tried to understand how the buck-boost converter were built. And then Arduino coding based on MATLAB language and the circuit diagram using Simulink were started. Our team decided that we need to research more deeply on PID and PWM, So we started studying more. At the end of the term, rewrote the winter term report. There are more technical research, and what we have done were included in the paper. In the spring term, our team planned finally to conduct physical wiring and with the microcontroller and to start debugging and collecting data. Unfortunately, due to COVID-19, we were unable to start physical circuit building. Instead, states of the project report and final written report were completed.
Displayed on this slide is the chart breaking down the general tasks assigned to members of the group. We chose Keen to be the leader of the group since he was the student who initially reached out to our advisor, Dr. Niebur, to carry out this project, along with gathering the members together to form this project group. For project planning, all members were involved in figuring out when tasks were due, so all members would have an understanding of when their parts should be done, along with when to expect other members' parts to be done to proceed with the project. All members were also responsible for doing research on their specific portions of the project, whether that research was on programming the microcontroller, assembling the circuitry, or understanding solar energy trends throughout the year. For single line diagrams, we chose Gus to work on these documents since he has had the most experience with single line diagrams involving solar components due to his co-op experiences. For simulation software and programming, the group chose Kyujin due to his studies in computer engineering and having the greatest understanding of these topics compared to the rest of the group. For controller design, we chose Kevin to work on this task due to his interest and understanding of signals and systems. And lastly, for physical circuit construction and testing, Keen and Tim were chosen for these tasks since they had the most hands-on experiences with the lab equipment in Basone along with the power labs.
This is our final budget that we bought for our project. We purchased 3 buck boost converters, one 10-foot 16 American wire gauge wire, a 4 amp circuit breaker, wiring connections, as well as 3 different types of digital potentiometers that we would incorporate in our buck boost. Our total spent on this was just about $120 for the whole project. This is our industrial budget that we calculated. We calculated the cost of salaries for engineers, rental of office spaces, software licenses for different softwares, as well as hardware equipment purchases. And after all of that, we calculated out the budget to be a total of just over $1 million.
Overall, for the 6 months our team was given to work on this project, much progress was made. To start, simulations for the microcontroller were completed in the middle of the winter term. The group gathered a general understanding of what would happen when certain parameters, such as input voltages and currents, entered the buck boost converter. In addition, the programming for the microcontroller has reached the point where it can be implemented into physical assembly and tested to remotely control the output voltages and currents of the buck boost converter. For the physical product assembly, analyzing the chips and testing out multiple input and output values for the buck boost converter were completed in the winter term. The manual potentiometers are ready to be removed and replaced by the digital potentiometers. After this, testing can be done. And lastly, the project budget for small-scale construction and assembly was completed for the products the group had expected to purchase. In addition, the expected industrial budget for this project was mapped out in case this project was to be carried out to become an actual product for households.
The future plans for this project would be for someone to assemble a group, and which then that group needs to be educated about what the project is about and what has been accomplished so far. Then constructing the prototype as well as testing the prototype. And once the prototype is completed, they can have further simulations tests with testing it on actual loads that can be used in a household setting. And these are our references. Any questions?